Hi, everybody. I'm really sorry for being gone this Thursday and Friday. So I thought I'd make a video going over something that I want you to have a firm understanding of when I get back, and it's something that I've alluded to earlier. Now, it might seem a little bit simpler than what we've been doing. Okay? Definitely more conceptual. But the reason we're doing this is to create a bridge between ionic bonding and covalent bonding. Now, we know that in ionic bonding, we have this electron, and it's fully transferred from somebody who usually has 4 or less valence electrons. Low binding energy gives it to the person with a higher binding energy. This person becomes a cation now, +1. This person becomes an anion, -1, and they're drawn together because of that positive and negative mutual attraction. In physics, they call that a Coulombic force. Not a real bond, it's more of an attraction. Now, although we've talked about the covalent bond, where the binding energy of the first element and the second element are both fairly high, so instead of both letting them go, they're going to play tug of war with them. We talk about this as being a very different real bond, and it's true. It's a very different real bond. Okay? But the mechanism is still the same. The only difference is there is not somebody with a low binding energy. So they play tug of war. The mechanism is the same, so we can draw what are called Lewis structures for both of them. And this is really going to bridge the gap between covalent and ionic. So when I come back on Monday, after you go through these notes, Eric is going to give you a worksheet, and I'd like you to work through that worksheet and make sure you understand that, and I'm going to give you a short quiz based on the problems you see in the worksheet. And the quiz will actually look just like the problems in the worksheet. Okay, so here we go. I want you to get out your notebooks right now, take some notes, and when those notes are over, Eric is going to give you the worksheet. You're going to complete that, turn it back into him. Sound good? Miss you. I'm probably, God knows where. I'm up in the sky somewhere right now, flying to the Middle East, hopefully getting some sleep. All right, so here we go. The first thing that we've alluded to is this idea of valence electrons. These are the electrons that are responsible for bonding, and we're going to call these electrons the outer S and P electrons. And there is a max of 8 valence electrons. And we're going to do that in a moment. The Lewis dots are going to be, it's a model that shows valence electrons using cute little dots. Yay. In case you didn't know, that is a dot. Okay, so let's see some examples as to how to get the valence electrons. So sodium, since it's the outer S and P electrons, what we want to do is the electron configuration for sodium. So we're going to do the shortcut, helium, 2s2, 2, ooh, that's not right. Come on, silly Ramsey. I can do neon, 3s1. So the outermost S and P electrons, we see that there's nothing in the P orbital. So there is one Lewis dot. So the way I show that is I write Na, and this one becomes a dot right here. Yay! So sodium has that one electron available for bonding. Calcium. Well, where the heck is calcium on this silly periodic table? So let's look here, and let's look at the old Google. Yay. Okay, pull this dude up. All right, so calcium's right there, so that's going to be argon 4s2. So let's go back here. Calcium, you can see, even I don't have this stuff memorized. Argon 4s2. So we want to show those two electrons. We're going to do it this way, calcium. And instead of putting them right next to each other, since there's a total of 8, we're going to mix those S and P orbitals together. In college, you'll learn about that as a process called hybridization. Do these glass keep my coffee way too hot. It's ridiculous. Anyways, it's a process called hybridization. So we now think of them as 8 electrons. They came from the S&P orbital, but now they're just 8. So the first 4 are going to stretch themselves out, and then the last 4 are going to pair up. So in this case, there's just 2. Okay, that's the Lewis dot diagram. Carbon, helium, 2s2, 2p2. So the valence electrons are the outer s and p electrons. So there's 4 of them. Carbon. So like I said, one's going to go here, 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 here. Now carbon is such a versatile element because it can make 4 bonds. Sulfur. You know what? I need to go back and look here. So that's neon 3. All right. No big deal. So neon 3s2, 3p4. It's very common for people to think there's only 4 valence electrons in sulfur, but it turns out there's not. There's 6 because valence electrons are the outer s and p electrons. Now sometimes I like to circle these as a reminder that now they are paired up, and we have a name for these things. These are called lone pair electrons. They're not going to bond. The only ones that are going to bond are going to be these ones that are not paired up yet. We can think of those as those up arrows in the subshells. Neon's a noble gas, so we're not going to just say neon. That would be ridiculous. We're going to say helium, 2s2, 2p6, 6, 7, 8 electrons. So 1, 2, old bathroom rule, 3, 4, 5, 6. And you can see there's 4 lone pairs or 8 total valence electrons, and there's no unpaired. So this is one of the reasons why noble gases are not going to form any bonds. So let's go through now and let's do the Lewis structure for an ionic compound. So the first thing they do is they give you the ionic compound. Okay, and now what we're going to do is we're going to go straight to the Lewis dot diagram for each. So here, this is going to end in S2. So we know that magnesium is going to have 2 of those. And iodine is going to end in S2P5, so there's going to be 7. So I'm going to circle those. All right, so now we're going to do the formation and the formula. Okay, so now first off, we know that an ionic bond is going to happen because this would rather lose 2 and have S2P5 in that first energy level than gain 6 and have S2P5 in that S2P6, in that second energy level. So here, these things all have low binding energies in the examples that I'll be using, and these things here have high binding energies. As a side note, we're going to refer to this term binding energy as electronegativity when we get to covalent bonds. Okay, so the first thing we do is we draw them side by side. So Mg, this is going to be the formation part, okay, and I. And we're going to use arrows to show the transfer of electrons, and this is where it might become helpful to circle these. Okay, so these ones, low binding energy, are going to be transferred to the element with the high binding energy. So there's an empty space right there. So there is a transfer. Okay, but what we see now is we don't have anybody who's willing to accept this electron. So we need to bring another I in here. Now, yes, this is the charge switchy thing, but I want you to do it in terms of the Lewis dots. Okay, that's how I want you to do it for now. And that's going to go. Okay, so that is the formation, and the formula now is simply going to look like this. And here's how you're going to draw it in this case. You're going to draw Mg. How many arrows are leaving? All the Mg's total. In this case, this is each Mg. We're losing 2. That'll be 2 plus. And each I owns 8. So here's how you're going to show owning 8. You're going to put it in a bracket like this. And each I just took 1 arrow, but there are 2 of them. And this right here is the formula, the Lewis structure for the ionic compound. And no, again, it's not a bond, it's an interaction. Our little water friend can go right through there and separate it. Let's try aluminum phosphide. So we know that Al ends in S2P1, so Al is going to have 3. And P ends in S2P3, so it's going to have 5. 1 lone pair electron. So for the formation, I'm going to draw Al here, and I'm going to draw P here. And I see that these ones want to lose them because it's easier to lose 3 than gain 5. And this one wants to gain them because it's easier to gain 3 than lose 5. And this one's going to go here. This one's going to go here. This one's going to go here. It's a perfect match. So the aluminum, each aluminum, there's only one of them, lost 3. Okay? And this 1P gained all 8. So you notice this way of drawing it is really showing what's going on. And it gained, those 3, so it's minus 3. And that is the Lewis structure. I don't want you to write ALP. I want you to write it exactly like that. Strontium phosphate. So strontium ends in S2, and phosphide ends in, we saw it before, S2P3. So these Lewis dots represent those outer S and P valence electrons. Strontium, it's going to look like this. P, probably made these too big, but whatever. This, okay. So this one would rather lose 2 than gain 6, and this would rather gain 3 than lose 5. Therefore, the one on the left is going to have the lower binding energy. It'll be the source of those electrons. Boom, boom. Okay, but there's no one to fill that. So let's bring in another strontium. So there is that. Okay, but there's nowhere for that to go. So let's bring in another P. Oh, but there's no one to take that. So let's bring in another S. R. Oh, perfect. So each SR, that one lost 2, that one lost 2, and that one lost 2. And there's 3 of them. So each of the 3 SRs are 2 pluses. And there's 2 Ps. And each of those Ps got all the electrons. Notice that whoever owns the transferred electrons is getting brackets around it at the end. Okay. So 2, 3. Notice I'm always drawing using the bathroom rule. Each P, 1, 2, 3, 1, 2, has 3 arrows pointing towards it, meaning it accepted 3 electrons. So 3 minus or minus 3. Sometimes in chemistry we draw 3 minus. That's kind of silly. And that's the answer. Plus 6 minus 6. And this attraction is an ionic bond because we had a full trans... God, my handwriting is horrible. How do you guys even deal with me? Of electrons. Okay. And that's it. Bye. See you guys on Monday.